and another 4 basic functions. This is going to be the third installment to the 12 basic functions that we're going to be looking at. And as in the previous videos, what we're going to do is look at some parent functions and consider, do they have continuity? What is the domain? What is the range? Are there extrema? Are there asymptotes? Or are there other defining features in the graphs? Example 1, the absolute value function, f of x is equal to the absolute value of x. This notation you should already be familiar with. Interesting fact, this function has an abrupt change of direction at the origin. For the most part, you can look at the left side of the graph as being the line y equals negative x. At the origin, it switches directions abruptly and becomes the equation y equals x. All other functions that we would look at will be smooth on their domain. So this is the only graph that has this sharp turn within it. Continuity, yes it does. It is continuous over here, it's continuous here, and even at that abrupt turn, it does have the coordinate 0, 0. The absolute value of 0 is going to equal 0. Continuity is yes. The domain is going to be all real numbers. Okay, we got negative infinity to infinity. The range is going to be bounded below. It does exist at 0, 0, so we're going to use a bracket. We have 0, and it goes up to infinity. Extrema, yes it does. It does have an extrema here. It has a minimum at 0. Is it even, odd, or neither? This is definitely even. It is reflective across the y-axis. Example 2, the sine function, f of x is equal to the sine of x. Interesting fact, the name sine is a translation mistake that was made in the 12th century, but it lives on today. Okay, translation mistake, yet certain things catch on and we just continue to use them forever. Okay, I'm not going to bore you on the details of what the translation mistake was, but that's just a fun fact, and if you want to, you can go and look that up. Okay, here's a graph of the function. We've seen it before. It's just that wavy graph that moves through. It has high points at 1. It has low points at -1. Continuity, yes. This is a periodic graph that continues this shape forever. The domain is going to be all real numbers. The range is bounded. It is bounded below and it is bounded above. We would say that it is bounded. Okay, it does go as low as -1. And it goes as high as 1. Okay, this is the first function that we're looking at. That is a closed interval for the range. Extrema, this is a little bit of a weird one. It has an infinite number of extrema. Okay, it has an infinite number of local extrema. We do have them at maxes, which would be at 1s. We also have them at minimums at -1s. Do we have an absolute extrema? The answer to that would be no, because we don't have one location which is higher than the rest. We have a whole lot of them that just tie. Okay, so we do have local. We have a local max, which is going to be at a height of 1. We also have a local minimum, which is at -1. And we have an infinite number of these, as this is a periodic function. Okay, even, odd, or neither. Even, odd, or neither. Definitely not going to be even. Okay, you could just look at this mound right here. That does not reflect over there. Is it an odd function? Yes, it is. You can choose any point on this side of the graph. Let's suppose you choose that point. You can match it up with the origin, then pick out another point that is equidistant in the opposite direction, which would be here. Okay, so you'd have that point and that point with the origin as a midpoint, which of course is going to make the midpoint the point of symmetry. You could also choose this point with that point of symmetry here. You can choose this point with that point of symmetry at the origin. This is going to be an odd function. Example 3, the cosine function, f of x is equal to the cosine of x. Interesting fact, the local extrema of the cosine function occur exactly at the zeros of the sine function and vice versa. So basically you got the same thing as the sine function. except everything is going to be offset by 1/4 of a period. In the sine function, the graph passes through the origin here, moving in an upward direction. That will match up with this part here. The high point was located around here, which is going to match up here for the cosine function. So it's the same thing as the sine function, just everything is shifted over 1/4 of a period. And what the interesting fact is telling us is that the extrema in the cosine function, the high points are actually going to be intercepts of the sine function. The low points will also be intercepts of the sine function. So you could go back and do a comparison of the two graphs if you want. Does it have continuity? Yes. The domain is going to be all real numbers. The range is also going to be bounded -1 to 1, with including -1 and 1. Extrema, we do have a lot of local extrema. Local max at 1. And you have a local minimum at -1. Is this graph even, odd, or neither? Well, the previous graph, the sine function, was an odd function. But now that we've shifted it over, it's going to lose that characteristic. However, it does pick up the characteristic of being even. This graph is going to be symmetric about the y-axis. You have a low point here, you have a low point there. High point, all those are going to match up. This is symmetric about the y-axis, making it even. Our fourth graph is a bit of an odd one. This is the greatest integer function, which we're going to simply describe as f of x is equal to int, which is going to stand for integer of x. Okay, notation is a little bit liberal here, but we're going to use that to represent the greatest integer function. Okay, another way to describe this graph is also called a step function. Okay, it looks like we have a bunch of steps as we move through it. All right, as a graph, we don't tend to see this done too often. However, it does represent a lot of real-world situations. Those real-world situations might not be greatest integer, but it will be something that takes on what could look like this if you were to graph it, where you've got different levels, different steps to the function. Okay, so you've got these constant lines, but then it jumps to another one. Okay, you are going to notice that you have an open location with a closed location above it. We got to make sure that we don't have it closed underneath the other one. Otherwise, this technically fails to be a function. Okay, so a way to look at this graph is that at an x value of 1, you're going to get a y value of 1, and you're going to continue to get y values of 1 all the way up until you get an x value of 2. Okay, so like 1.1 is still going to give you a 1. Okay, 1.9 is still going to give you a 1. Once you get to 2, it'll jump to 2, and you'll continue to have 2 up until you get to 3, where it jumps up to the next. The interesting facts I've probably already mentioned: this function has jump discontinuity, and it has jump discontinuity at every integer value of x. Similar looking graphs will be called step functions. Does it have continuity? Absolutely not. It has jump discontinuity between every integer. It has an infinite number of jump discontinuity, which we would also refer to as non-removable. The domain, okay, even though we have a lot of discontinuity, the domain here is going to be all real numbers. There is not a value of x that the function fails to give you an answer. Okay, take any of the little steps here. At 1, you get a 1. At 1.1, you get a 1. 1.2, you get a 1, and so on. Once you get to 2, it just happens to jump up to 2. Okay, but there is always a value that you can plug in for x. The answers you're going to get back are always going to be integers, though. All right, for the range, this is where we got the problem, because as you look from the bottom to the top, you've constantly got these jumps in values. Okay, but let's think about the outputs that we get. For this, the outputs are going to be all of the integer values. That's what it's going to be. Okay, so for the range, interval notation isn't going to really work well to describe this. What we could do is just write a simple statement. We could say that the range is the set of all integers Okay, we could say that the range is the set of all integers. You could even use set notation if you want for this. I think that that statement works out pretty good though. Even, odd, or neither. This graph is definitely not even. It is not reflective across the y-axis. Is it an odd function? Let's investigate that one a little bit closer. Okay, if it is an odd function, the point of symmetry is going to be located at the origin, which would be here. Okay, now consider just one point along that step if you go out to 0.5. Okay, now for this to be an odd function, that point would need to match up to a point on the opposite side of the point of symmetry, which would be here, and that does not exist. It does not exist there. So this will not be odd. This will be neither.
Later, blah.